Hello students, today we're going to have a look at section 5.3 which deals with independent events and the multiplication rule of probabilities. This is also something that you have covered before. This is the last of the things that we've covered before as we move into section 5.4 and beyond. In chapter 5 we're going to see a lot of new material and a little bit more challenging stuff, so kind of buckle up for what's coming. That'll be next week. So today's section 5.3, independence and the multiplication rule. And what we're going to be looking at in this section is to identify independent events. Again, something that you've done before. Use the multiplication rule for independent events and compute at least probabilities. So 3 little skills that we'll look at in this section. And so let's jump right in and define what independent events are. Two events, E and F, are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. Okay, two events are dependent if the occurrence of event E in a probability experience affects the probability of event F. So let's talk about an example of each of these kinds of things so you can kind of work it through in your head. Let's suppose that we have a bag of 6 red marbles, 5 blue marbles. Let me write this down for you. 6 reds, 5 blue, and 3 green. Okay, so event E, let's say event E is, we're talking about probability of drawing a red marble. So if event E is drawing a red, then the probability of a red is just basic 6, 5, and 3. That's 4 or 6 out of 14, which we would simplify or could simplify into decimal form, or 3/7 as a fraction. All right, so let's say that event E is drawing a red marble. Let's say that event F is the probability of drawing a green marble after drawing a red marble. Okay, so if we draw the red marble and then replace it, right, if we put it in the bag, if we draw the red marble and put it back in the bag, then the probability of G is going to be 3 out of 14. Okay. So if we draw the red marble and don't replace it, if we keep it out, okay, if we draw the red marble first, the probability is 6 out of 14. If we keep the red marble out of the bag and then draw a green, then the probability of green changes to 3 out of 13 because the one marble was kept out. So in the instances, the 2 instances that we look at, if we draw the red marble and replace it, put it back in the bag, then the probability of drawing a green is independent of drawing a red, because the probability of a green, if we drew green first, would be 3 out of 14. The probability of a green, if we drew green second, would still be 3 out of 14 if the marble is replaced, the first marble is replaced. But in the event that we drew a red, probability of drawing a red and then drawing a green without replacement, the probability changes from 3 out of 14 to 3 out of 13, and so we have dependent events. So the top example here is an example of independence, where we replace the marble and the number of marbles stays the same, and then the bottom shows a dependent event because the occurrence of the first thing happening changes the probability of the other. And we'll look at some more examples of that. But let's look at this. So there's 2 events here. We want to determine if these 2 events are independent or not independent or dependent. All right, so suppose you draw a card from a 52 card deck of cards and then roll a die. Are these independent events? So does the card that we draw have anything to do with what's going to happen on the die? And the answer is absolutely not. Okay, these are completely independent Okay, they're independent, and if you were writing this out, you would want to say they're independent because, right, the card draw has no effect on what happens to the die. Okay. All right. So this is a great example of independent events. These two things are completely unrelated to each other. All right. So let's look at another example. Suppose two 40-year-old women who live in the United States are randomly selected. Okay, because of the number of 40-year-old women in the United States, and because they're randomly selected, we can assume, or we should assume, that these two women have absolutely nothing to do with each other. All right, they're not related to each other. They don't live in the same circles. Are the events that woman 1 survives the year and woman 2 survives the year independent? So if the first woman lives, is there any way that her living affects woman 2 living? Okay, and again, because they're randomly selected and because there's no personal attachment to these two people, we're going to assume that woman 1 surviving the year has no effect on whether woman 2 survives the year or not. And so again, we would say that these two things are independent, and they're independent because of their lack of relation to one another. Okay, so randomly selected from a large number, we can assume no influence. Now, here's another example that's a little bit different. Suppose two 40-year-old women live in the same home. Are the events woman 1 survives the year and woman 2 survives the year independent? And this is an example where, I really don't love this example, but it's the example that the textbook gave us, so we can assume that there's going to be some problems and questions like this in homework and test questions that come up. Because they live in the same home, okay, we can assume that there are things that could happen to woman 1 that would affect woman 2. For example, woman 1 gets the coronavirus. She survives, but she gives it to woman 2, and she does not. So her survival has a direct effect on the other woman's non-survival. Or they got into a domestic disturbance, and woman 1 kills woman 2. Woman 1 survives the year, but woman 2 does not survive the year because woman 1 survives. So if they have a close proximity to one another, then we can assume some kind of entanglements that could cause these two things to definitely be dependent events. Okay, and so the close proximity is what makes letter C different from letter B. So that's independent events or not independent events. All right, so how do we use the multiplication rule for independent events? We already kind of looked at one event just a moment ago, but here it goes. If we want the probability of E and the probability of F, the multiplication rule for independent events, if E and F are independent, then the probability of E happening and F happening, okay, is equal to the probability of E times the probability of F. All right, so if they're independent, you just multiply the two probabilities together. Okay, so here we go. The probability that a randomly selected female aged 60 years or older will survive the year is 99.186%, according to the National Vital Statistics Report. What is the probability that two randomly selected 60-year-old females will survive the year? Okay, now we're going back to our example just a moment ago. Randomly selected, right? Randomly selected. We can assume that they have no association with each other, and one's survival is not connected to the survival of the other. So the probability that the two randomly selected females will survive, okay, so let's say the probability that female 1 survives, and female 2 survives is going to be equal to the product that female 1 survives times the probability that female 2 survives, which is going to be equal to 0.99186 times 0.99186. So it's 0.99186 squared, which is going to give us 0.9838. So there's a 98.38% chance that both females will survive the year. The 60-year-old randomly selected females will survive the year. Okay, so let's look at how this might extend to a different scenario. A manufacturer of exercise equipment knows that 10% of their products are defective. Okay, so the probability of a defect, the probability of a defect is equal to 0.1. And they also know that 30% of their customers will actually use their equipment. So the probability that the equipment actually gets used is equal to 0.3. If there is a 1-year warranty on the equipment, what proportion of the customers will actually make a valid warranty claim because of the defect? Now, here we have to see if there's any tie between defective products and use. And I think that we can, because defective happens at the plant, right? If it's defective at production, then the customer use has nothing to do with the defect. So we can say that these two events are independent. So if a person, so what we're asking here, or we can also assume that if the person never uses the equipment, then they will not know that it's defective. If they never use it, then they're not going to make a warranty claim. So we're assuming that the people who use their equipment are going to discover the defect. Okay, so the probability that a valid warranty claim will be made is going to be equal to, so we're probability of a defect and use is what we're looking at here, is going to be equal to 0.1 times 0.3, the probability of the two things happening, and that's going to be 0.03, which is interesting, right? 10% of their products are defective, but only 3% are ever going to come back because most exercise equipment never gets used or doesn't get used enough to discover the defect. So that's pretty interesting. 0.03 is what we're looking at there for a probability of a warranty claim being filed. So this company may not be very concerned about fixing this defect. It's only going to affect them very little. So 3 out of 100 things that get sent out. So all right, let's look at the next one. This next thing is just like the other events that we've looked at with the sums of probabilities. In the OR case, if the multiplication rule for independent events extends if we have multiple events that are independent. So this doesn't work if we're just looking at two things. It works if we're looking at any number of things. So let's revisit the first example that we looked at. Okay, the first example that we looked at, the probability that a randomly selected female aged 60 years old will survive the year is 99.186, according to the National Vital Statistics. What is the probability that 4 randomly selected 60-year-old females will survive the year? So this probability that 4 will survive, okay, so what we're saying is that female 1, female 2, female 3, female 4, randomly selected, again, so we can assume independence between these 4 females is going to be, so the probability that 4 females survive is going to be the product of those 4 females' individual survival rates. So 0.99186 to the 4th power. Okay, 0.994186 to the fourth power is, I don't have that. Let me go back. Let me go back to that page there. Grab my calculator. 0.99186 to the fourth power is 9678, and then some other stuff. So about 0.9678. Let's do this since they carried it out to 5 decimal places. Let's carry it out to 5 decimal places ourselves. So 96.784% chance that 4 randomly selected females will all survive the year. It's kind of ironic, right? We're talking about surviving the year in this coronavirus outbreak that's going on right now. So we've got a 96.784% survival rate. So the interesting thing that takes place here is we'll notice that, if this was 5 females that we were talking about, then the only thing that's going to be affected is that exponent there. So we could talk about the probability that 500 females would survive. And as you can see, as the number gets higher and higher, this value is going to continue to get smaller, right? The probability that 4 females will survive the years is lower than the probability that only 1 will survive the year. All right, so let's look at how this might extend to computing at least probabilities, okay? At least probabilities. So let's look at this. The probability, again, that a randomly selected female aged 60 years old will survive the year is 99.186%. What is the probability? Okay, what is the probability that at least one of the 500 randomly selected 60-year-old females will die? Okay, at least one will die. Okay, what we're going to have to do here is go back to our complements that we looked at yesterday. Okay, or in the previous lesson. I don't have any idea what day you guys would look at this. So what is the complement of, I'm going to let you think about this, at least one will die. The complement of at least one will die. If at least one will die, what are we saying? What's the complement of at least one? Okay, so hopefully what you are coming up with here is the complement of at least one will die. At least one will die. The complement of that is that none will die. Okay, that's the complement of that event. So the probability that at least one dies is going to be equal to 1 minus the complement that at least one dies. The complement of at least one will die is that none die. Okay? All right, and so the probability that none die is going to be equal to 0.99186, 500 people. Okay? So we use our trusty calculator, 1 minus 0.99186 to the 500th power, and we get 98.320%. So there's a 98.32% chance that at least one person out of 500 randomly selected 60-year-old females will die in the course of a year. So that's what we've got to look at there. So at least one, right? At least one, the complement of that is that none will die. And that's what you kind of have to do to figure this out, because it would be really complicated to find all the probabilities of 1 person dying, 2 persons dying, 3 persons dying, 4 persons dying, and then combining all of those probabilities It's much easier to just say that the complement of at least one will die is that none will die. And then you can use the complement rule to get that. All right. So here's a summary of the rules of probability. Sum of all probabilities of all outcomes in a sample space must equal 1. We've got if E and F are disjoint events, then the probability of E or F is the sum of the probabilities, and that extends to multiple things. If E and F are not disjointed events, then it's still the sum of the probabilities, but we have to subtract the intersection of the probabilities. We've got that. And then today we looked at if E and E complement represent the complement of E, then probability of the complement is 1 minus the probability of E. And then today we said that if probability of E and F is equal to probability of E times the probability of F if the events are independent. And then that's going to extend in the next lesson as to what happens if events are dependent. So your homework for 5.3 is page 262, 1 through 8, 11, 12, 17, 18, 24, 27, and 28. Again, you can ask questions on the message boards or shoot me an email or text if you have questions about any of these problems. Again, I want to caution you guys, take this seriously. There will be a test coming soon, and we'll spend some time together face-to-face somehow, FaceTime or something like that, to get prepared for that event. All right, have a great day. Hope you guys are well. I'm praying for you and looking forward to seeing you again soon.